Hello and welcome to the second video on our section 10.2, which this video will focus primarily on the second derivatives for parametrics and what that can mean. So let's talk for a second about why we need to take the steps that we do. Normally, when we're looking for a second derivative, we would just simply take the derivative of the first derivative and we arrive at the second. But now there's this extra step in here that we need to do, and we need to divide by dx dt in order to get the accurate second derivative. So let's just pause for a second and try to figure out why we need to do that. So when you had a function y equals, and it's some function in terms of x, some Cartesian mode equation there, and we did the first derivative, then that's the derivative of y with respect to x, and over here is still some function, right, in terms of x. Well, if we go to do the second derivative, and maybe some of you didn't realize why this was, but we're going to take the derivative of that derivative with respect to x. And this is how, and it's still some curve or function in terms of x, right? But this is how you come up with the notation, because some people just think the 2's are kind of in the wrong place when you write out the second derivative notation like this. It's because you see here there's two d's, right? So it looks like d squared y, which is read the second derivative of y with respect to x twice. You have two dx's. So that's what talks about concavity, right? Concavity. Sorry. So that's what talks about the concavity or shaping of a curve, whether something is concave up or concave down, which we can still study in parametrics. So let's take a look at the same thing in parametric modes. Let's start with a blank slate. And let's look at if I now have x equals some function of t, right, and y equals some function of t, because we're in parametric mode. My first derivative is still dy dx. That's how I arrive at the slope of the tangent line per the previous video, which is actually dy dt over dx dt. And we talked about why that works, because really when you have that, you're dividing by that fraction, you multiply by the reciprocal, and there the dt's will divide to 1, so I'm left with dy dx. So taking this idea, let's now take the derivative of this first derivative, right, with respect to x. But really, my input is not going to be x's. Because if you think about it, this is dy dt. So this is some curve, right, with t's. And this is some function over here with t's. So this is not going to be a dx down here. These are actually with respect to t, because you're taking the derivative of what you got with respect to t. For example, if x equals 3t squared and y equals 6t cubed minus 1, your dy dx is going to be your dy dt, which is 18t squared, over the dx dt, which is 6t. So this derivative is in terms of t. So when I look at that, and I'm doing the derivative of that function there, that first derivative, I'm going to still have it be in terms of t's. So that's why, just to start this off, I have the first derivative of the derivative, right? So derivative of a derivative will get me the second derivative, but now nothing is going to divide out. So what I'm left with here is I do have the d squared y part like I want, the second derivative of y, but now I have over dx and a dt. That is not what we want. So we need to multiply, right? Because again, I want this to say the second derivative, which is normally d squared y over dx squared. So I want this to say this down here. So I need another dx in the denominator. That's an x. and I need a dt in the numerator, so those divide out. Well, when you're multiplying by dt over dx, that means you were really dividing by dx dt. So in order to come up with the actual second derivative of y with respect to x twice, I'm going to have to not only take the derivative of the derivative that I found, but we also have to divide by that additional dx dt. Okay? So let me show you how this looks. And there's just a few different interpretations or way to write it. So I'm going to find the first derivative and the second, and sometimes this is going to take a little bit of algebraic manipulation to make it look good. And then I'm going to use that to answer the question, for what values of t is the curve concave up? And we should know that a curve is concave up when its second derivative, right, second derivative of y with respect to x twice is greater than 0. So that's when I'm concave up. So, all right, so I'm going to say here's my x, here's my y. I need to find dx dt. So that's just e to the t. And dy dt, and I do write these out separately. I'll show you why here in a second. That is going to be a product rule. I'll take the derivative of t first. That's 1. So I leave e to the negative t alone. Plus, and I'll leave t. And then I'll do the derivative of e to the negative t, which is e to the negative t times negative 1. So I'm going to change my plus in the middle here to be minus. Okay, I'll show you again here in a second why I keep those separate. So for my first derivative, right, dy dx, I put the numerator as the dy and the denominator as the dx. Okay, that looks complete. But I would tell you that if you think you can combine, which you usually can, or if you think you can simplify that first derivative, you should do that before you go on to the second derivative. That is just good, efficient derivative taking that you hopefully learned and mastered in Calc 1. So the more complicated of a curve that you have to work with, the harder the derivative is going to be, and the harder the solving is going to be later. And we don't want to make it any harder than it needs to be. So let's do a little bit of algebra here and focus in on that. Okay, so what I'm going to do is I'm not going to separate and reduce. I think you certainly can, but many of my students right now are rewriting this as e to the negative t. So I would, oops, that's a dx. I keep doing that. So this is a dx. It's not letting me change it, but it is. Here we go. So it's dy dx is, and so I will say it's e to the negative t times my numerator. And I can distribute that in. And so really, my first derivative, which I think will be neater, is e to the negative 2t, right, because you add your exponents when you're multiplying, minus t e to the negative 2t. I certainly could factor something out if you wanted to. If you are better at quotient rule, then certainly you could rewrite this if you wanted to, because if I factor out the e to the negative 2t, it's 1 minus t. So I could say any of these are equivalent. So it doesn't matter to me what you work with. It needs to be organic to you. But here's a place where I'm going to maybe take the derivative from, or here's a place to take the derivative from, or here's a place to take the derivative from. Personally, I would recommend the yellow or the green, but again, either one is fine. So what's important to note is that as I am ready for the second derivative, I'm going to go right to, I have the second derivative of y with respect to x twice. I am going to take that second derivative, or in other words, the derivative of what I have, and I'm going to work off of the yellow and then turn it into a fraction. But then I'm going to divide by dx dt. And that is why I found it really important to write these out separately from the beginning, is because you're going to have to go back and use that in the future. So I'm going to divide by this additional e to the t. Remember, that just makes it so I have with respect to x twice. So in the numerator will be the derivative of my derivative, so the derivative of the yellow. So that's chain rule, so negative 2e to the negative 2t. And product with chain. So I'll be careful. I'll do the derivative of that t first. So it'll be negative e to the negative 2t, and then negative t times negative 2e to the negative 2t. Okay, and I am going to absolutely make this look a little bit nicer and expand this out. So second derivative of y. I can combine these two terms, so that's negative 3 e to the negative 2t. This will become plus 2t e to the negative 2t, and it's all over e to the t. Again, I am not sure that that's something that you want to work with algebraically. This is technically a fine second derivative, but if we're doing something with it, we may want to go one step further. So again, I can factor out the e to the negative 2t. That's 3 plus 2t, which now I can use my negative exponent rule here. This is going to be 3 plus 2t all over e to the 3t, because this would be now e to the t times e to the 2t. Add your exponents. So here's, I think, a very much nicer second derivative to work with. And they want to know overall for what values of t, so that's kind of nice because I can stop at the t equals part, right? So for what values of t is the curve concave up? So now I'm going to take this second derivative and figure out where it is 0. From our rational functions from Calc 1, I really only need that numerator. So this is what I will do. I will set my numerator equal to 0 to find all the places where the second derivative is equal to 0, and then I will use that to assess, just on a basic number line, where is the second derivative greater than 0. So I can subtract 3 and divide by 2, the t value, right, which is going to make that second derivative equal to 0, and that t value is 3/2. That's where my second derivative is equal to 0. So now I'll do a little bit of side work again, and I'm going to do a number line, and I'm going to label this number line that it is my second derivative, so that I'm recognizing that this is assessing concavity. I don't necessarily have other bounds for, start and stop, so sometimes you want to pay attention to that. This is where it is 0. And then I just test a number on this side and maybe a number on this side to see if my concavity is positive or negative, just using that second derivative test that we learned in Calc 1. We certainly could use technology to help us with this, but I think having a linear second derivative is not going to be all that bad to work with. Remember, this is really what we're looking at here, because the denominator, e to the 3t, will always be positive. So if I'm looking back here at my whole second derivative, I'm not really concerned with the denominator portion of that. So if I plug in a number less than 3/2, so on this left-hand side over here, so something like -2 or -3, if I put that in, I do get a negative value. So think about -3 plus 2 times -3, right? I do get a negative value, which means on this side I'm concave down. And if I put in a number like 3, because that's easy, I have a positive, right? So that means on this side I'm concave up. And so the values where I'm concave up, there were no other limiting factors for t, so I would say I'm concave up 3/2 to infinity. And that would be a description of that parametric curve. And you can certainly check this graphing the parametric on your calculator, which again was in the other video. Okay, so this next question, I started it and then I'll have you pause the video and get to a certain point, and then I want you to unpause it and check it so we can kind of work on it together without having a, hour and a half long video here. So for which values of t is the curve concave downward? So we're really answering a similar question that we were answering before, only now it's concave downward instead of up. But I still need second derivative. And now it's giving me an interval. Because typically with trig functions like cosine or sine, we may have circular type or cyclical curves. I'm not saying that they look like the normal sine and cosine waves that you've seen before, but we could have cyclical curves, and we want to limit the interval in which we're looking just to make it easier to write our answers. So I found dx dt using chain rule. I found dy dt, and here's my first derivative. Most people stop here, or some recognize, oh, well, I have a negative divided by a negative. Oops, I'll put that back in. So they take that out, but otherwise they leave this alone. And I will say I need you to really pause here and ask yourself, is there anything that you can do that will simplify this first derivative? You should have the most efficient simplified first derivative that you can to work with. I can still use identities for this first derivative to simplify it further. I will want to keep this for potential domain restrictions or for potential problems. I also want to make sure I keep dx dt visible, because to find the second derivative we always have to divide by dx dt. But I really feel like on your way to your second derivative, you should have the most simplified first derivative you can. So the identity that I will use is the double angle identity for sine, which many of us are comfortable with. I just wrote it down. And so my derivative, this is still first derivative, would be sine of t over, this will now be a 4, because 2 times this 2. Right? There's a 2 in the problem, but the double angle has an additional 2 in it. So 2 times 2 is 4, sine t cosine t. Sine t over sine t does divide to 1. Again, I'm not talking about domain right now. I have the original if I ever need to talk about the domain of the derivative. And so dy dx is 1/4 secant t. And a lot of people do not ever get here, and so their second derivative becomes a lot more difficult to work with. They need a lot more identities, and they have a very difficult time solving it, I'm not going to lie. So we're going to pause the video. I want you to try from here to find the second derivative, and then let's unpause and you can match. Okay, so I have found the second derivative over here, highlight it in blue. So the second derivative of y with respect to x twice, I took the derivative of 1/4 secant t to be 1/4 secant t tangent t. And then you have to divide by the additional dx dt. Again, don't try solving this and setting this equal to 0 to talk about concavity. Simplify it first. So let's try that, and then again, when you think you have a simplified, go ahead and unpause. Okay, so let's see where you're at. So I have the 1/4, so I just wrote a big fraction bar and I put 1/4. This orange boxed secant of t becomes basically a reciprocal of cosine t, so I put cosine of t in the denominator. Tangent of t, I highlighted that in yellow, that becomes this sine of t over cosine t. And then in the denominator, kind of put that bubble around it, the -2 and then sine 2t. We talked about that earlier, the double angle for sine, so that this becomes -4 sine t cosine t. So the sine t's do divide to 1. And then I have cosine times cosine times cosine. So if you'll excuse me, I have cosine cubed, or -1/16 secant cubed t. I lost that third one. So here's one, here's one, here's one. Right, so I have cosine cubed, and the -4 times 4 gives you the -16 in the denominator. So now if I'm finding concavity, normally you would say find your second derivative, which I would go from right here, and set this equal to 0. And so what I find from here is that I have no points of inflection because there are no places, remember inflection points are where you change concavity from your curve. Well, there are no points of inflection because I can never have the second derivative equal to 0. I can never have a 0 in the numerator. I have a -1 in the numerator. But that does not mean that you never change concavity. We change concavity potentially anywhere in our second derivative where we have a domain restriction. Remember that? Whether it's removable or not, we just want to check it. So I will look here. My initial raw, that might be too dark, but my initial raw derivative for second derivative looked like so. So I want to take a look at all of the places for my second derivative. So when I'm making my second derivative number line test, first I'm limited 0 to pi, right? And then I want to look at all the places where I either have a point of inflection, which I don't have any, or I want to look at any restrictions to that domain. And I can even see from the most basic level from my first derivative that I have issues anytime sine of t is going to equal 0 and anytime cosine of t equals 0. And we should know that those are those quadrantals. So although I'm not technically testing anything over on this side of 0 and over on that side of pi, we're not going beyond that. I may want to just check to see if my concavity does change at 0, but it was non-inclusive anyway, so I'm not going to include those boundaries anyway. But I do want to add in here pi over 2 because the cosine of pi over 2 is 0, so I can't have that. Okay, so now I just need to test these sections here, and again, how you decide to do that is up to you. I'm going to work off of this yellow second derivative that I just highlighted here. So for example, if I think of, a value inside of here, I might be thinking something like that, right? And if I put it into the second derivative, right, this is where my second derivative value would be. I just need to determine if it's positive or negative. You don't need to get too fancy here. Cosine in the first quadrant is positive. You cube it, it's positive. Times 16, it's positive. So I have -1 over some positive number. This will be negative. Again, if you need to watch that a few times, I apologize for my speed. Then, if I check something between pi over 2 and pi, I'm in the second quadrant. So maybe I'm 3 pi over 4 or 2 pi over 3. Regardless, you're in quadrant 2. That's a negative value. A negative value for cosine, and then you cube it, you're negative. So now I have -1 over a negative number, which will turn positive. So while I was concave down to begin with, then I changed concavity and I'm concave up. So I can safely say that in the interval that they asked me for, oops, did I want up or down? And I highlighted it. I am concave up, where I just went to right, but they want to know where you concave down. So I'll write that concave down 0 to pi over 2. And again, had they asked you where you were concave up, you would say pi over 2 to pi. Okay, now let's talk for a minute about horizontal and vertical tangents. We have talked about horizontal tangents quite often. It's where the tangent line is horizontal. So that's where our first derivative is 0, right? Horizontal. Okay, now in order for a fraction to be 0, we just kind of touched on this a minute ago. In order for a fraction to be 0, I need my numerator to be 0, assuming that dx dt would not be 0 at the same time. Okay, well then pretty much exactly the opposite is true for a vertical. I can have a vertical tangent as well. If I think about dy dx being the first derivative, Now that's where I'm trying to divide by 0. So some numerical value for dy is found, but that's where your dx is going to be 0. So what does that mean? Well, in parametric, I have a separate dx dt as I do dy dt. So for example, in this one, find the points on the curve where the tangent is horizontal or vertical, and then I can graph it to check. My dx dt, like I said, is separate from dy dt. So if I'm looking at dx dt, it's just negative t. And if I set this equal to 0, t is 0. Those aren't points on the curve, though. I'll talk about that in a second, right? Because I'm trying to find points on the curve. So I need the actual x and y values here. But that is the t value that is going to make my tangent line vertical. Because dx dt is in your denominator, and dividing by 0, 1 over 0, we know to be a vertical asymptote. So I'll put t equals 0 into x and y to find the points on the curve. So at t equals 0, so x will be 2 minus 0, so x is 2, and y will be 0 minus 0, so y will be 0. So I am vertical at 2, not too bad, right? So let's do the same thing for the horizontal. That's going to be my dy dt, which we should be able to take fairly simplistically here if I don't make an error. And now when I solve this equal to 0, I'm looking at horizontal. Right, where is my tangent line horizontal? So I'll add 4 and divide by 3, take the square root. Now be careful, it is plus or minus, right? When you're solving that quadratic, you have the two solutions there. And so I will write this as plus or minus 2 over rad 3 is the t value. This is going to be a little bit messier. You can leave it the square root of 4/3. If you are squaring everything, you may want to do that. It doesn't matter. Whichever way you decide to work with it is fine. So now if I want to find points on the curve, and if I want to keep them exact, again, keeping this, plus or minus square root of 4/3 might just be easier. It's up to you. So I have t equals negative square root of 4/3 first. So x equals 2 minus a half times this negative square root of 4/3 squared. So the x actually isn't going to matter whether I use positive square root of 4/3 or negative, because you're squaring the t. 2 minus a half times 4/3. So it's 2 minus 2/3, or x equals 4/3. Okay, now I'll do the same thing for the y. So it's t cubed, I'll write it down, minus 4t. So my t is negative square root of 4/3 cubed minus 4 times the square root of 4/3. So this is, if I cube it, this is a square root. So I'm going to end up with one whole one of these times its square root, right? And then minus 4 of these square roots. So I can combine like terms if you see it. They're both so many square roots of 4/3. So I have negative 4/3 and negative 12/3, so negative 16/3. Or if you take the square root of 4, you get 2. Negative 32 over 3 rad 3. I don't care how you write it. It's the same point. So it's 4/3. This is for horizontal. And then this negative, I'll just leave it, 16/3 times 4/3. So 16/3 times 4/3 is 4/3. times square root of thirds. But I also have to do the positive square root of 4/3. So pause your video, try it, and then you can compare. Okay, so if you're looking at t equals the square root of 4/3, put that into the x, you do get positive 4/3, which was the same as when we put in the negative square root of 4/3, so that should be good. And then if you put it into the y equation, you should get negative 8/3 because it's 4/3 of the square roots minus 4 of the square root, so you can combine like terms. That's 12/3, so you get negative 8/3 of that square root, or negative 16 over 3 rad 3. Again, however you want to write it, you have a numerically equivalent expression. And then let's take a look at the graph and make sure we verified that we are correct. So again, when you go to your calculator, please make sure that you are in parametric mode, because that's what we're dealing with here. And when I go to parametric mode, I want to type in the original x and y that I had from the given problem. So I'll click my y equals here, and I was in radian mode as well. So if you're working on trig problems, that's going to be important. And then I'll go to my y equals, and I'll type in the 2 minus 1/2 t squared and t cubed minus 4t. I will always hit window because, again, if you've ever hit zoom standard in here, it takes you back to that t min and max that may or may not make sense for your problem. We definitely need t values that are negative, but they're not all that big. So, I mean, you can not limit it. It's not going to show necessarily all of these, but I'm going to just go negative 10 to 10 for t. But I want to keep my t steps small because I like to see curvatures. And again, I think it's going to be hard to see your concavity if you can't see a curvature. So that 0.13 number for me, again, it's based on pi, but that's fine. In viewing window, I'll get a look and see. Sometimes you'll want to make it smaller or larger just depending on where your curve is. And again, this looks to me like maybe a little bow tie or ribbon, or maybe some of you, if you're a cancer survivor out there, good for you. There's your ribbon, right? It's kind of on its side. Or maybe you're learning to tie your shoe, or not learning. Maybe you're teaching your kid to tie their shoe, right? There's your shoelace. There's your loop that you're trying to make. So if we look at it, where my pen is, I'm trying to draw it right here. There is this vertical tangent, right? And I'll show you how to help calculate this in a second. And then I can see a horizontal tangent at the bottom of that sort of loop and at the top. So what I'm going to actually show you is how to, now that we already have the algebra on our side, I'm going to go to second calculate, and I can calculate a value. Notice this calculate menu is going to get smaller and smaller as we go through the different modes that we have on our calculator, but calculate a value, and it allows me to type in the t value. So I can say, well, I thought at t equals 0, that's where my vertical tangent occurs. And that appears to be exactly where I think it is. Again, t equals 0 corresponded to the point, rectangular point, 2, 0 is what we found. So that worked out. Then I can calculate it again. I can calculate a value, and I can say negative, and I'm just going to leave it all under the square root, because sometimes it's just easier to type it in that way as well. 4 divided by 3, and I again apologize for the speed of my calculator. It's a project for maybe tomorrow. Hit enter, and it'll show you, and it'll also give you good estimates for the rectangular point that you should be noting. So that was where we said the x was 4/3, and then you could write this decimal down for y and make sure it matches ours, but it definitely does. And there's our top horizontal tangent, and then we could also do the same thing, calculate a value for the positive square root of 4/3. And we would see the other one. So again, it doesn't necessarily draw it for us because I'm not asking it to. I'm just asking it to show me where those points are on this curve, or on this loop, if you will. And then I can see if that's a horizontal tangent or not. So that's one way to verify that. Okay, the next topics are going to be dealing with integration, so I'm going to make another separate video for that on parametrics. So we're going to study areas, arc length, and surface area. I highly recommend before you watch the videos on parametric area, arc length, and surface area that you re-familiarize yourself, if necessary, to the rectangular or Cartesian mode of area, arc length, and surface area, because I think if those topics are sort of fresh in your mind, then you will do better with them in parametric mode. So I will make that video coming soon.